So I'll tell you what, now it's showtime. It's 1:30, so let's go ahead and do this. So let me hit the record button. And now we are officially recording at 1:30 on March 20th, 2021. And this is Professor Cummings, and we were going to do a problem that was recently in the mechanical design class. So I was on planetary gearing, and I thought this might be something good for my YouTube channel as well as for my students to see. So I just have to double dip here a little bit. So let's go ahead and put this in presentation mode. And we are off. Okay, so now we've got this set up. And I'm going to put my pad and pen in, so we will see what I'm doing. We are currently being recorded, so I think that's going to be good. So this is our first attempt at being sophisticated. Okay, here we go. Alrighty, so let me go through this problem. So we have a problem here that I gave to the class. Let's go through this. And this was basically for you to learn planetary gearing. And we're going to be using the tabular method of planetary gearing. And let's state the problem here. So a company has developed a new portable well drilling rig and has a planetary gearbox as a transmission, right? So it's able to drill through a variety of conditions. So that means clay, really packed soil, sand, whatever type of conditions you might find as you go through several layers of soil in order to get to the fresh water. All right, so the operator will be able to shift to any gearing configuration to adjust the given conditions using the 5 laws of gearing. So in this particular instance, we've got let me get my pen here. I got to get my pen here. So what we have is we have a ring gear with 45 teeth, a sun gear with 30 teeth, and the planet carrier, and the planets just happen to have 15 teeth. The speed on the motor, the specification on the motor is it's 200 RPM, and it's got a torque of 120 Newton meters and a power of 24 kilowatts. So that is basically our situation, what we're trying to do. So let's see, what are the questions that are involved? So these are the questions I gave the class. The first question is, what is the maximum output torque of the system? So you're going to have to be able to figure out what the maximum output torque, what configuration will give us our maximum output torque. 2, at that torque, what is the reactionary, what is the input gear, and what is the output gear? Number 3, what is the highest output RPM of the system? Number 4 is a little odd. In a revised design, they're adding a second stage of planetary gearing. So it's going to be a 2-stage, goes from a 1-stage to a 2-stage system. And this second stage is identical to the first, meaning that you've got the same ring, same sun, same orientation, same planet carrier. And they're stacked in series, so there's a collinear series of gears. So what is the highest torque value of that the new system can achieve? And number 5, what is the highest RPM for that new system? All right, so we got our 5 questions. Let's go through this. And keep in mind we're using the tabular method of planetary gearing. If you remember, a couple other videos for those who are watching, and if you're in my class, we've gone through this several times. What the planetary gearing system is. Again, you got the first step in developing this table with the arm fixed. The gear 2 makes gear 2, which is the sun, makes a goes 1 unit rotation counterclockwise, and here is what the calculations. The arm is fixed. You're going 1, so we could say RPM, and the ring gear is operating based on that ratio, going in the opposite direction, because the arm in the planet is just basically an idler gear. So the input, which is N2, which is the sun, and the teeth on N4, which is the ring, this would be the ratio between the two. Now, when you look at step 2, we've replaced that 1 with just a value of x. So this is the ratio. So basically this is just taking 1 and looking at the ratio in terms of some unknown x. So when we look at all elements are rotation, with y also in rotation, about y, and then we look at the total motion. So then these are the carrier, the sun, and the ring all operating in concert with one another. So we've got a series of equations, and really what we're really worried about are these final equations at the end on number 4. So we've got a carrier rotation, we've got a rotation that represents the sun, which again, you're looking at the relationship between the carrier and the sun. That's how you're measuring it. And then you've got, this is the carrier in motion, or arm in motion. And then you got the ring, again, which is the arm minus what the ring is doing. So again, those are the 3 equations, and they work together, and we can get all 5 of the 5 laws of gearing taken into account. We can make calculations based on any one of the inputs and outputs to figure this out. And remember the 5 laws of gearing. If the carrier is the input, the carrier is the output, and then the planet and the ring, are either one is stationary, one is, whatever, correlating. If the carrier is the output, the ring or sun is the input. If the carrier is the output, either the ring or the sun are the input, but one has to be in the reactionary mode. Then of course you got neutral, you've got reverse, and you've got direct drive. So those are the 5 laws of gearing: overdrive, underdrive, reverse, direct, and neutral. So we want to figure out what is the maximum torque. The maximum torque is typically in, here we go. The maximum torque, what is the maximum output torque of the system? And that is typically in an underdrive condition. And since you have carrier is going to be the output, so that means that either the sun or the ring have to be the input, right? And that'll give you, it'll step down your speed, but it'll step up the torque. So there's an inverse relationship between the amount of torque you can get out of the system and the RPMs you get out of the system. All right. So at the highest torque, the carrier is going to be the output, which means that the carrier is unknown. Y is the carrier value. These are the, the gear teeth. The ring is 45. The sun is 30. Our motor speed is 200 RPM, and our motor torque is 120. So what we're going to need to do in order to answer both of these questions is come up with a velocity ratio in this condition. And once we figure out what one is, we can use that velocity ratio to figure out what the other is to answer the second question. So in this condition, we're looking at a situation where the ring is going to be reactionary and the sun is going to be the input. So when the ring is reactionary, we got our equation that covers what the ring is. So y minus x times the ratio between the number of teeth in the sun and the number of teeth in the ring. That's going to equal 0. Because that's, you can call it reactionary, you can think of it as stationary, being stand put. So looking at that condition, you know that y is equal to x times the ratio between the sun and the ring. Now with the sun, since we know that the sun is going to be the input, that means the sun is tied to the motor speed. Sun is actually tied to the motor, so the motor is going to be influencing directly onto the sun. And when we look at the equation for the sun, that means x plus y is equal to 200 RPM. All right, so x plus y is 200 RPM. We still don't know what y is, but we do know that y can be put in terms of x, and that's going to be important, when we start to deduce this, because really what we're doing is simultaneous equations. So we do need to know what the ratio is between the sun and the ring. So the sun is 30, the ring is 45, and that means that the ratio is 0.67. So a 2/3 relationship between the two. So now we can take this value, this ratio, and plug it into this equation here for the ring, or y is equal to x times the ratio of the sun and the teeth, since we have the ratio of the sun and the teeth, or the sun and the planet's teeth. And we can plug that back into this equation. So what we'll have is one unknown. We'll have just x will be the only unknown in this equation, and we can calculate and get a value of x. So we got x plus 0.67x is equal to 200, which means that 1.67 is 200, so x is going to be 120, and that means we can figure out what the carrier speed is. The carrier speed is, again, equal to y, and we have y is equal to 200 minus x, which comes out to 80 RPM. Again, that's best. All we did was take this equation and subtracted x from both sides. So 200 minus x. So 200 minus 120 is 80 RPM. So now we have the speed of velocity of the carrier, and that's 80 RPM. We can take that velocity ratio. So the output is 80 and 200 is the input, RPM. So that comes to 0.4. So we answered the second question already, that the reactionary is going to be the ring, the input is going to be the sun, and the output is going to be the carrier. So now we need to know what the output torque is, and this is where we use this velocity ratio. So again, remember there's an inverse relationship between the input, or the speed, and the torque. So if this went from 200 to 80, so this means this is going to step up the torque from 120 by 0.4, as that rate with the ratio of 0.4, which means the output torque is going to be 120 Newton meters divided by 0.4, the velocity ratio, and that's 300 Newton meters. So based on the gearing system we've developed and the motor we've selected, we're able to step this up to 300 Newton meters of torque on this drill. So that's the most torque we're going to get when we're plowing through packed dirt, packed soil, or dry clay, or anything else that might be in the way. So let's see, what was question number 3? What is the highest output RPM? So again, we're going to the highest output, so it means that we're going to step up from 200 using this same system. And with that, y, the carrier is going to be going 200. The ring is going to be a reaction, or a carrier is going to be the output. Oops, sorry, this is a flaw here. Oh no, my mistake. All right, so the carrier is the input. So when the carrier is the input, we're in overdrive. So that means the carrier is 200. So the carrier is tied to the motor, right? So the carrier is the input. So that means we have a value for y. We have the ring is going to be reactionary or stationary. So this equation, y minus x with the ratio of the sun to the planet, or the planet to the ring, is going to be 0. So the ring is going to be y is equal to x times this ratio of the sun teeth to the ring teeth. And the ring is going to be 200 minus 0.67x. And that works out to 298 RPM for the value of x. So if we want to know what the sun is, the sun's rotation is going to be x plus 200, which is the output, and that means it's going to be 498 RPM. Now in this case, the velocity ratio, which is output over input, is 498 over 200, so it comes out to about 2.5. So the output torque in this system is going to be 48 Newton meters, but the question was, what was the RPM? And that's at 498 RPM. So 498 RPM. So let's go ahead and just make sure that we state that clearly. So we actually solved the problem at that point, but we do know what the torque is. And for those who aren't normally in my class, this is what I normally tell my students to do, is to just to work through the problem all the way for that particular condition, and they usually end up filling out a table. So let's see. So now we have the next stage, or the next problem, where we actually add a second stage to the system. So let's see here, and then you got a bad slide. All right. So in a revised design, a second stage of planetary gearing, which is identical to the first, is stacked in series. So we have a collinear gearing system. What is the highest torque value of the new system, and what is the new system can achieve? And the second question is, what is the output RPM of system 4? Alrighty, so our system in question number 4. So we've got two questions here. So remember, they're identical. So that means the ratio between the sun and the planet is going to be the same. That means all the calculations are going to be the same. So if we're trying to get maximum torque, that means we need to go into the highest underdrive, or an underdrive for stage 1 and underdrive again for stage 2. And that's what's going to get us the highest torque we'll possibly get. And also, when you're looking at these stacked gears, the train value, or the value for the entire system, is the product of the velocity ratios. So the velocity ratios for the first system is, again, 0.4, and that gives us an output torque of 300 Newton meters. So when we look at this entire system, or you can call it its own gear train, the velocity of the first stage and the velocity of the second stage equals the train value. So that means you've got a train value for this entire system of 0.16. So the output torque, and again, this should, I wish this hadn't come up before, but the output torque of the new system is 120 Newton meters off of the motor, divided by the train value of 0.16, which is 750 Newton meters. So it went up more than doubled the output torque when we put these two systems together. Now the RPM for the new system, again, that's just multiplying the RPM of the motor times 0.16, which is 32 RPM. So you can see it went from 200, again, this is a double underdrive, so 200 to 32 RPM, 120 Newton meters up to 750 RPM. And that's using the tabular method. Now I didn't leave it in a table, but I just took the equations out of the table and just knew the 5 laws of gearing as we needed it. So let's see. So this is what I wanted to show, and I was kind of learning as I went through the entire system, to see how things were going. And I wanted to also see how to use this software. Let's see. Let me shrink you down. And looks like we have one person watching now. Okay, so that is our problem. So I'm going to go ahead and call it a done deal. And I will see you guys later. I'd like to thank you for watching my first live stream, so you guys could be here for the experience. Let me stop recording here. And this is Professor Cummings, and I